Alice, Bob, and Eve explain quantum ansatz.
I've been working on this jigsaw puzzle for hours. I think I have an idea of what the final picture should look like, but I'm not completely sure. I have put some smaller groups of pieces where I assumed they may later fit in.
You know, what you're doing is similar to using an ansatz in quantum computing.
Ansatz? That's such a fundamental concept in quantum algorithms, especially for NISQ-era devices.
What's an ansatz? And how does it relate to my puzzle?
An ansatz is essentially an educated guess about the solution to a problem. In quantum computing, it's a trial quantum circuit with adjustable parameters that we tune to find the answer we're looking for.
When you start with a rough idea of what the final picture might be, that's your ansatz. You're making an educated guess based on the pieces you've connected so far.
So in quantum computing, you start with an approximate circuit and then refine it?
Exactly. For many quantum algorithms, especially variational algorithms like VQE or QAOA, we start with a parameterized quantum circuit, which is the ansatz, that has a structure we believe might lead to our solution.
Think of each parameter in the ansatz as being like the position of a puzzle piece. We don't know the exact right position immediately, but we can make adjustments until things fit properly.
How do you know if your ansatz is getting closer to the right answer?
We run the circuit on a quantum computer, measure the results, and calculate how close we are to our goal. Then we use classical optimization techniques to adjust the parameters and try again.
It's like how you're testing different arrangements of puzzle pieces, measuring how well they fit together, and then making adjustments based on what you learn.
But how do you know what an ansatz to start with? There must be countless possible quantum circuits.
That's where scientific intuition and domain knowledge come in. For chemistry problems, we might use ansatzes, inspired by the physical interactions between electrons. For optimization problems, we might choose ansatzes that can represent constrained solutions.
It's like how you looked at the picture on the puzzle box to guide your initial approach to the puzzle.
I see. And I'm guessing the quality of your initial ansatz greatly affects how quickly you find a solution?
Absolutely. A good ansatz needs to balance expressibility, the ability to represent diverse quantum states, with trainability, the ability to be optimized efficiently.
Too simple an ansatz might never represent the correct answer, like trying to solve your puzzle with half the pieces missing. Too complex an ansatz might be impossible to optimize effectively, like having too many similar-looking pieces mixed together.
So quantum scientists are essentially creating educated guesses about what quantum circuits might solve their problems, and then refining those guesses through measurement and feedback.
That's it exactly. And it's particularly important for today's quantum computers, which are too small and noisy for more complex algorithms, but can run these variational approaches effectively.
So every time you work on a jigsaw puzzle, you're essentially practicing the same problem-solving approach used in cutting-edge quantum algorithms.
Wonderful! How cool is that?